Work is force times distance. That's nothing new. But what if the force is not constant? What if, instead of graphing out like this, force as a function of distance, and as you travel through the distance, the force is constant, then force times distance is just that. It graphs out as a rectangle. This is the work done. But supposing the force was not behaving as nicely. Most forces actually, imagine pushing somebody on the swing. You make contact initially, the force rises to a peak value, and then gradually drops away as they swing away from you. That area is still the work done, but it's not as simple as just multiplying the peak force times the distance, because you did not apply the peak force the entire time. We're not going to worry about that. What I want you to be concerned with today is this. When you pull a spring, the force increases. It starts small, and the further you pull the spring, the bigger the force gets. So what's that graph going to look like? Picture it. Obviously, if the distance is the stretch, if the distance is equal to the stretch, then when there's zero stretch, there's zero force. And obviously, as the stretch increases, the force increases. So later on, we have more force. The only question is, what does it look like when it goes from here to there? Is it curving this way? Is it curving that way? Is it a straight line? I would argue that it must be a straight line, because spring scales, if you look at the numbers, they're evenly spaced. If the force didn't increase in a linear fashion, then scales would have to have markings that were not evenly spaced in order to be calibrated. So, if the force increases in this fashion, then we can say that the force is equal to a constant times the stretch length, x. Every straight line that goes through the origin, there's a slope times x plus a y-intercept of 0. So if the force is equal to k times x for springs, then we can say what the area is. The work done has to be equal to the area of that triangle. But we know how to find the area of triangles. Area is equal to 1/2 the base times the height. Well, the base of that triangle is just the stretch length, x. And the height of that triangle is the force, which is equal to k times x. The peak force, I should say, not the force is obviously changing the whole time. But the force at the end, the height of that triangle, is the peak force, k times x. Therefore, the energy stored is 1/2 kx squared. X times k times x times 1/2. That's your energy stored in a spring. Or in fact, anything you can stretch that behaves in an elastic fashion. So, here's what we're going to do with it. I want you to get a drinking straw. I have a whole bag full of these, so if you don't have access to drinking straws, I can mail you one, and I'd be perfectly happy to do it. Take some nice sharp scissors, cut off the bendy part. You're going to want some Scotch tape and some paper, and make some fins at the back. Cut a little notch. Make sure that the fins line up with the notch for reasons that we'll see shortly. For the tip, if you have some Play-Doh or soft clay, about yay much makes a pretty good tip, but it occurred to me that people might not have Play-Doh at home. Another possibility, I took a small carpentry screw, and for safety, I wrapped the head of the screw in a little bit of tissue paper. So there's a nice soft tip at the end. Nevertheless, safety first. So you build your dart out of the non-bendy part of the straw, you cut a notch at the back, you tape some fins on the back, and you tape the head of the dart to the front of the screw. Okay? What we are ultimately going to do with this is take the elastic, put it over the end of a ruler, notch the dart into the elastic band, and the reason you use a ruler is so that we can measure specifically how far we have stretched that elastic band, because obviously the further you stretch it, the faster it goes when you let it go. The fins and the tip are to make sure that the straw flies straight, and the first thing we're going to do to gather data with this is we're going to try pointing the ruler straight up. You measure. You may want to put a bit of tape on the end so that your rubber band stays on the tip of the ruler. You measure how far the elastic reaches unstretched, and we're going to measure the stretch length in terms of how much extra you have to pull it down. And in a separate video, I will launch the dart straight up in the air, and we'll see how high it goes based on how much we stretched it. And from that, we will test this formula that energy stored is 1/2 kx squared. Once we have that lab done, then we'll be able to actually target things with the dart. So this is our final project. We've got, I think, 5 classes left at this point, and we'll talk more about this later next week.